finish my slides. Hi everyone, very glad to be here. I'm Peter, I work in PyTorch at Facebook and MemoPart. I'm here for GTC this week, which is tomorrow. That's why, so some of these slides are also from my GTC talk. That's why they have a lot of references to NVIDIA and GPUs in them. I'm also still a bit jet lagged, so my brain is kind of running in 8-bit quantized inference right now. So yeah, I work at Facebook. This, on the left is a picture of Mark Zuckerberg with me in that order. I'm not just at Facebook, but Facebook AI Research. So that's this lab here on the right. It's actually a really old picture from like 2 years ago. We're probably about like 4 or 5 times the size now. We just doubled in size last year. This person in the front is still Jan LeCun, who you probably all know. He's still leading the lab, and then there's really a whole bunch of really influential people in the field. We're winning a lot of really awesome prizes. I think both best paper and best student paper at last CDPR, best paper at EMNLP last like 2 weeks ago. So really doing very influential and basic research. And so this talk is going to be about PyTorch. I could also just show this slide and then actually end my talk, but I do have a couple more slides after this. Okay. Oh, sure. So yeah, as you can see, people do like PyTorch very much. It's been very popular ever since it started. So it's about 1.5 years old now, and we're maturing quite rapidly. And I also have some numbers to actually show you just how much we're maturing. So I'll start a little bit by like introducing what PyTorch is. I don't assume that everyone has worked with it before, so I'll just talk about how it's different from other frameworks in the field, and then talk a little bit more about what we've been doing to make PyTorch more production ready over the past year, and also some of my own work, which I'll talk about in the latter part of the talk. So first of all, what is PyTorch? So PyTorch is a machine learning framework that was born, so some of these have changed, but it was born with an emphasis on eager execution. So I'll talk a bit more about what this means, but generally it means that if you write a PyTorch program and the interpreter runs through the lines of your code, of your program, it actually executes those lines on the fly, which means you get results as your program executes, which is much more flexible and much easier to work with. Then we also focus on dynamic neural networks. So this eager execution means you can really execute the wildest possible models, and I do have some examples of those, so that we really don't have any boundaries on what you can express with PyTorch in terms of neural networks. Also GPU acceleration, so just kind of like with TensorFlow, GPU acceleration is at the core of PyTorch, since we generally care more about GPUs than we do about CPUs and machine learning these days. So that's really important. We also have really awesome support for our distributed training, actually in a very different way than something like TensorFlow does it, which kind of just expects you to hand off your graph and does everything for you, whereas we give the developer a lot more control and like a lot more primitive interfaces, which people have liked in the past very much. And then kind of an overarching theme about PyTorch is that we, since we have Py in the name, we kind of follow the Pythonic principle of preferring simplicity over complexity, and if there's many ways of doing things, we prefer the simplest one. And generally, you'll notice that PyTorch really feels very native, very natural to Python programmers, and it really feels like it's like a part of the language itself. And we care very much about that in everything we do. So first of all, like what is PyTorch for? So generally we try to enable things. So PyTorch enables research. Here's one nice number from just last week. We had around about 250 mentions at iClair, which was just 87 last year, so that's a pretty big jump. And that's compared to 260 mentions for TensorFlow, so we're almost pretty much there. And TensorFlow had 250 last year, so the growth is quite at a different scale, which we're quite excited about. Then we also enable ecosystems, so there's a huge number of projects built on top of PyTorch. I think there's something like 120,000 lines of import torch on GitHub right now. So on the top left is a framework called Pyro, which is for probabilistic programming. Then Horovod, which is a distributed training framework. Both of these are built by Uber that also supports PyTorch. And then the LLNLP library from the LNAI Institute is a natural language processing library built on top of PyTorch. And so these are external, and then internal we also have a whole bunch of things part of the PyTorch umbrella. So there's, if you go to GitHub, pytorch.org/ELF, which is kind of like an OpenAI Gym sort of reinforcement learning environment framework. Then Translate, which is the code Facebook uses to do some crazy amount, something like 3 billion machine translations per second on the Facebook platform. So you can check out that code, which is built on top of PyTorch. And then there's also a project called Glow, part of the Umbrella, which is a machine learning compiler that takes an abstract representation of a machine learning graph and then compiles that for fast hardware like TPUs or other kind of accelerators. And then lastly, of course, we enable lots of partners. So there's a huge number of both industrial and academic labs using PyTorch. So there's the industrial ones in the top, NVIDIA, Uber AI Labs, Twitter, Salesforce, and many others. And then on the academic side, we have really most of the big universities, so Stanford, Carnegie Mellon, Pierre et Marie Curie University in France, NYU is really big, Oxford is really big. So we have a lot of people who enjoy PyTorch, who contribute to PyTorch, and we really try to support them as much as we can. Yeah, so getting a bit more technical, in this slide, in the bottom left, I mentioned eager execution, and this is kind of the core differentiator between PyTorch and other frameworks, so I want to dive a bit deeper into that and get a bit more technical. First of all, who are the kind of players between these two? So there's eager mode on the left, eager also known as imperative execution, and then static execution on the right, or also known as declarative. So in the eager world, we have Chainer, which is a framework written by some developers in Japan, Dynet, which I think is from Carnegie Mellon, which also has eager execution, and then of course yours truly, PyTorch. And then on the right, the big white elephant in the room, of course, is TensorFlow for static graph frameworks, MXNet, which is Amazon and Apache, and Caffe2, which until now has been the production-ready framework Facebook is using for, I think, something like 3 trillion predictions per second across all different domains, from vision to language to speech, and which actually recently merged into the PyTorch framework. So we're doing a lot of work to kind of leverage the benefits of both PyTorch and Caffe2 in a new framework. And yeah, so to kind of exemplify what the difference between these two modes of operation is, I have these two examples. This is not a real programming language. It's kind of a fictitious one I made up. But I think it showcases quite nicely the way these execution modes influence the programming model that you have in Python or whatever language you're interfacing to these libraries with. So the first thing you'll notice at the very top is that in the static mode, your shapes have to be known ahead of time because you're constructing a graph and the graph has to be correct. So the framework needs to know the sizes of your model. So in TensorFlow, you can omit the batch size, but generally you need to specify what the shapes are because the graph has to be checked for correctness. And in an eager mode framework like PyTorch, which really cares about dynamism, there is no such necessity. So the shapes and sizes can be anything. They can change at runtime, which is really awesome for natural language processing, for example, where you can have different sentence lengths and change those at runtime. So that's really as dynamic as it gets. Then the next line is the execution. And what's really important here and very different is that in the static mode framework, when you do something like d equals s times a plus b, d will not actually be a value, right? It'll instead be some kind of abstract handle to a node in a graph, which later on you can execute to produce that value. Whereas in an eager mode framework like PyTorch, when you execute this line, d is actually a value. It's actually something like 5, or it's a tensor. It's actually values that you can inspect, that you can change at runtime, that you can really look at and debug. And this is kind of a really important difference because it means that in something like TensorFlow, you're not actually programming, you're actually meta-programming because the code you write isn't actually executing or producing a result. Instead, the code you write produces a graph, which then, when executed, produces a result. So you're actually programming a program, which is the graph, instead of programming code itself. Whereas in eager mode framework like PyTorch, you're coding directly. Another really important difference is around control flow. So in a static mode framework, because you have to essentially embed the control flow into the graph, you can't just use the language's native control flow. Instead, you have to use some kind of if clause operation, which will then, when executed in the graph, perform the branch, which is usually really unintuitive and unnatural to work with. Whereas in an eager mode framework, because you're just writing code that gets executed on the fly, you can just use the language's native control flow. So you can just do normal if clauses, and at runtime, it'll take either the true or the false branch. And the same goes for loops. So you don't need any kind of fancy, unintuitive while loop construct where you pass some function and some condition. You can just write normal while loops, and that's really easy to understand and a lot more intuitive. And then, of course, ultimately, the difference, the big difference is that at the end of the static mode execution, you have a graph, and then you have to evaluate that graph in some session environment to get the result. Whereas in an eager mode framework, this value here at the end is just a value. It's a tensor, you can look at it, you can change it, you can debug it, and it's a lot easier to understand, I think. Especially for research, because research is all about reducing the latency of mapping the idea in your head to some visualization to a result. And in a static mode framework, there's kind of this extra hop you have to have in your head of going from the idea to the graph to then to the execution. So I think eager mode is a bit easier for that. And so just to recap, in both cases we started with a program, but in the eager mode we go from the program directly to the result. And as a side effect, which is also actually a really important implementation detail, we also get a graph. And so the way this works is that when we execute an eager mode program, even though we're producing values, so even though D is a value, we're also internally recording that S times A happened, and S times A plus B happened. And so at the end of this program, we both have result, but we also have a graph. And programs or frameworks like PyTorch, for example, use this graph to then do automatic differentiation. So once we have this graph, we can walk it in reverse to compute gradients. Whereas in TensorFlow, for example, that happens differently. You just have a single graph, and then gradient nodes get added to it. So this graph is in eager mode is there, but it's kind of hidden and implicit. Whereas in a static mode framework, you have a program, and then you get to a graph, and only from that graph do you end up getting to the result. So there's this extra hop involved compared to eager mode execution. And so kind of to recap the pros and the cons, so in an eager mode framework like PyTorch, you have no boundaries on the flexibility, so you can express anything you want to. So for example, one of the more complicated models we have running in production at Facebook is one that does like recursive tree traversals. So you can imagine you have some kind of syntax or parse tree for a sentence, and you want to traverse that recursively. Good luck doing that with a static mode framework. Whereas in PyTorch, for example, that's just normal code. You can just do normal recursion. So there's really very little boundaries on the flexibility. The debugging experience is much happier because you can just insert PDB wherever you want. You can just insert print statements wherever you want. And then the last point is kind of not as relevant to TensorFlow, but if any of you have used Theano in the past, you were used to having to get coffee every time you compiled your graph. So of course, there's no such thing in an eager mode framework because there is no compilation step. At the same time, the cons of an eager mode framework is that it's harder to optimize because there's no graph that you can hand to the framework for it to look at in its entirety. And that also makes it harder to deploy because when you want to deploy a new version of your model, because your model is actually code, you would have to deploy a new binary, whereas in a static mode framework, you can just ship your graph as like a JSON blob to the execution engine without having to redeploy anything. And then for static frameworks, it's kind of the mirror image of this, so it's easier to optimize, easier to deploy, easier to do post-processing steps like quantization. But then on the other hand, it's harder to understand, much harder to debug, and a lot less flexible. And what's kind of important here to notice is that the top left quadrant, which is the pros of eager mode, and the bottom right quadrant, which is the cons of static, are actually exactly what you care about when doing research, right? You care about not having any boundaries to implementing your idea, not having any boundaries to debugging, not having any like expensive steps in there. Whereas the top right and bottom left is what you care more about when you're doing inference. So that's kind of one thing to have in mind. Whereas also both, in this case, both PyTorch and TensorFlow are actually trying to get the best of both worlds. So just for those people who have never actually seen PyTorch, I think it's always kind of useful to understand what this thing actually looks like. So I'm just going to show what a typical example in PyTorch would look like. So we define a class, which is a neural network module in PyTorch, which gives you all the basic infrastructure you need. And then we have all the typical layers you would also have in something like Keras, right? We have convolutions, dropout, so on and so on. And then usually a model like this would have a forward method, which implements the algorithm that your model performs, in which case here you just compute the model. And then, of course, again, because this is eager mode, I can just print x in here. And when I execute the forward method, I'll get a nice tensor value with a current result of that tensor. And then other things we have in PyTorch, which are kind of important, are data loaders. So we have a mechanism to, in a multi-process way, load data from some data source. We also have a huge number of data sets built into the library, most of the big vision library data sets like ImageNet, Elson, you name it. So we have data loaders, which are a big important step, and then also basically the training loop, again, is very simple. There's no like a session involved like there would be in TensorFlow. You're just looping through the data set and then executing your model, and all of this is happening at runtime, so there's no separate graph involved or anything like that. Just to kind of give you a taste of what PyTorch looks like if you've never seen it. The next section is going to be about what we've been working on a lot over the past year, which is taking PyTorch, which kind of already has established itself as almost the go-to solution for research now because it's really friendly and flexible, but has not been as friendly towards production. So we've been doing a lot in this space to make PyTorch a better option for also deploying to production in bare metal, low latency environments. So I'll talk a bit about what our strategy is for that. So in general, as I've already mentioned, PyTorch, in PyTorch, your models are Python programs, which makes it really intuitive and native. It makes it easy to understand. It makes it debuggable. You can use print statements. You can use GDB. It's also really hackable because you can use any other Python library. You can use NumPy, SciPy, whatever gets the job done. You can do web requests inside your model. You can really do anything you want to. And that's really nice for research, but it does have some issues when it comes to production. And that one of the big problems is because we love Python so much, that can actually be a problem for production because oftentimes production means no Python environments. But whereas the normal PyTorch, as you have it right now, actually needs Python to run, right? And shipping the Python interpreter to a bare metal server, for example, would be kind of tricky and kind of cumbersome. You probably do not want to do that. It's also very difficult to optimize because, again, in an eager mode framework, you don't have a graph that you can look at in the framework ahead of time and do optimizations on. You also can't just like automatically parallelize it because the code is running as you execute it. And so we kind of want to change or like provide an addition to that. However, we also want to keep this PyTorch as you know it, as you love it. So in the future, we're just going to refer to PyTorch as it has been in the past as PyTorch Eager Mode. And then in addition to PyTorch Eager Mode, we're also introducing what we call PyTorch Script Mode, in which we kind of define a subset of the Python language that we can understand in a compiler. And then we allow you to write programs in Python, but with a subset of Python, which basically means you can still write normal while loops, you can do if clauses, but you can't like do a web request in the middle of your model because that would be hard to compile. But then the script node, as you'll see, we are able to optimize and compile, which means you can deploy it to production with no Python involved, and we can optimize it and do things like operator fusion and other cool things that you want to do for optimization purposes. And so how do we get from this eager mode to script mode? One thing we've cared very much about here is to make this transition very like flexible and very step-by-step. So if you start out with a PyTorch model that you do research with in eager mode, we want you to be able to in very small steps transform that into a deployable model. And the reason for this is really that most of the models you'll be writing for research, you'll end up just throwing away because they don't work or because there's something wrong with them. So there's really a very small subset of those models that you end up wanting to deploy. And for those models, we want to make it as easy as possible to go from the eager mode, from the research world to the production world. And the two mechanisms we have for that are the TorchJIT script annotation, which is a function annotation that you can add on top of a function, which kind of lets us know that we can look at the source code of the function, actually parse the code in there, turn it into our own abstract syntax tree, our own intermediate representation, and then do advanced compilation on that. And then the other mode, which is kind of simpler, but a lot less powerful, is what we call TorchJIT trace, which I'll show in a second, which has some limitations around control flow, but is actually a lot easier to begin with. And I'll talk about that right now. So what we do for tracing is that we, if we have some kind of function like this one here, which is a PyTorch function, which operates on some tensors, we have a TorchJIT trace function, to which you can pass your PyTorch implementation, and then some example inputs. And then what we'll do is run that function a single time with those example inputs, and then record a graph of all the operations that happen, kind of what we do for the backwards graph, but in a different way. And then we can simply take that graph that we recorded and then do optimizations on that. And so one important limitation about this is that it does not work well with control flow, right? Because if we have an if clause in this function and we pass it an input that takes the true branch, then all we see in the execution is the true branch. So we don't know that there was an if clause, and the graph that's produced wouldn't contain the if clause. It would just contain the true branch. So this mechanism, while it works really well for things like convolutional neural networks or generally straight line models that don't have control flow in them, it doesn't work for things like RNNs. And that's why we have the second mechanism, which I'll talk to in a bit. But it's exciting because it means that we don't actually have to change our eager mode code. We can just, so if this function would be just a normal function in your PyTorch model, you don't have to change anything about it. You just have to give us some example inputs, and we'll create a graph from that, which is really easy. And this works for simple functions like foo, and it also works for huge models like ResNet-18, which we can also just trace and produce graphs from. And then the second mode, which is kind of a bit fancier, is like an annotation mode, where essentially you tell us that, for example here, a module or just a simple function is written in the subset of the Python programming language. And then we know that we can look at the source code and actually understand everything that is inside this function. So for example here, this means that we know that you're not doing any fancy or like things that we can't understand, but you can still do things like control flow, and then we can look at the source code and understand that there's a for loop inside and really embed that for loop into the graph. So we parse the code, we look at the code, and understand that there's a for loop, and then embed that into the graph, which means control flow is preserved as opposed to tracing where it's not. So in this case, what's also nice about this is that it's really easy to go back and forth between what we call the script mode and the eager mode. So if, like later on in my research, I decide I do want to tweak this a bit more, and I do want to go back to the benefits that debugging and like printing gave me in eager mode, I can just remove this annotation, and then everything runs in eager mode again, and then I can add it back, and everything runs in graph mode again. So I can really switch between the two very easily, which allows me to make this path from research to production very smooth. And again, you can also combine tracing and scripting, which means for those models where tracing is possible, like for convolutional neural networks or like really like straight line models, you can use tracing, which is generally a bit simpler to use. And then for the ones where you need control flow, like RNNs or anything like that, you can use scripting, and you can combine the two. And then the end result, which you care about when you're doing inference, is that you can take this graph that we produce either from a trace or from the compiled script code, and then serialize that into some kind of representation that we have internally. And then in your production service, so this could be like some really bare bones C++ server, you can load this model without any Python dependency at all. So we provide a pure C++ library that understands PyTorch graphs that you can load this module into and then execute on tensors. So we have a really nice tensor library in C++. It's really awesome. I wrote most of it. And then you can execute this model using like data that you get from some web server or anything like that. And there's no Python dependency at all, so it's really lean and really fast. And yeah, and that's kind of the end goal of this research to production step, and it's pretty smooth, or at least we try. And so just for reference, like I mentioned that we have this custom language. We really can't think of this as a language in its own right. So we really do have like our own parser, our own compiler, just like you would have for a C++ compiler. So we do also have to implement everything we provide to the user here. And so what we provide at the moment is tensors and numeric primitives, so like floats, integers. You can use those like in PyTorch. Then if statements for control flow, simple loops like for loops and while loops. You can still use nn.module, which is kind of the basic organization unit in PyTorch. You can use tuples, lists. You can still use print statements, which still has some nice debugging features. And you can also still do gradients. What we don't have at the moment, which a lot of people in my team are working on very hard, is the general concept of mutable tensors. So you can't like mutate a tensor in this script code right now, but that's actually like a pretty hard problem from a programming language perspective, and we have a couple like PhD students working on this right now. So that's coming hopefully very soon. And then we also can't use the existing like ecosystem of PyTorch models yet, so we can't use like the nn.conf that we provide in PyTorch. So we have like our own internal like script versions that you can use, but you can't use everything that exists in PyTorch at the moment. But that's work that we're working very hard on. And then we also still have to do some more work to make gradients work inside the script mode. And so all of that is coming in what we call PyTorch 1.0 stable. So we just released kind of what we call the preview version of PyTorch, and then by NIPS of this year, which is in sort of December, we want to release like the final stable version where we like incorporate all the feedback we get in the months until then, and then we want to have those features as well, which will make it a lot more complete. And then the last part that I want to talk about is kind of what I work on myself, which is the PyTorch C++ interface, which might be interesting for some people who do research in more constrained environments, but it's also really interesting for people who just want to extend your Python models with something like a CUDA kernel for some like fast image operation, or for example, say you find that OpenCV has a really cool function, but it's only implemented in the C++ version. How can I use that in my Python program, in my PyTorch models? And a lot of the stuff I work on is making that really smooth. So I'll mention that very briefly. So overall, what we're trying to do here is like paving pathways, right? So we have a pathway from research to production. We have a pathway from eager mode PyTorch to script mode. And then we also provide a really smooth pathway from Python to C++ and also from C++ back to Python. And that's what this is about. First of all, let me give you like a bit of a brief overview of what PyTorch looks like in the back end, which is actually really a huge C++ library, even though it doesn't look like it from the interface we provide. But what we have at the very basis is a high-performance CPU and GPU-enabled tensor library. So you can see an example of this here on the right. So we have tensors, which you also saw you could use to execute your serialized PyTorch models earlier, where you can do operations as you couldn't do them in Python. Then on top of that, the PyTorch library adds automatic differentiation. So this means our tensors can now require gradient, which means we can do reverse mode automatic differentiation and restore gradients. And this also means, we have a dot backward function which does this automatic differentiation for you. And we have all of that in C++. And then on top of that, we provide two ways of extending PyTorch. The first is what we have, what we call C++ extensions, which is this mechanism of writing custom C++ functions or custom CUDA kernels and then binding those into Python. And then the second thing is kind of a bit of a bigger beast, which is a pure C++ front end, which is really an equivalent of the PyTorch interface, but purely in C++. And one, just like as a heads up, why this is actually useful, because you think Python is always the better option. We actually have some teams at Facebook AI Research that do research for the StarCraft game. And so, of course, in StarCraft, you have a pure C++ game engine with like really high frame rate, and they want to do reinforcement learning in this game engine, so they can't have any Python there, of course. So they want to do research in C++, and they, of course, because they're also scientists, they don't want to deal with like all the nastiness that C++ can throw in your face. So we provide a really, in my opinion, intuitive and Python-like interface in C++. So I'll mention very briefly. So first about C++ extensions, I'll show why this is interesting and how this is simple. So going back to the idea that you want to call some function OpenCV and then bind that into your Python model, this is actually really simple. So here's a small example. So we're in a C++ program. We include the Torch extension header and the OpenCV header. And then we can write a small function using this A10 library as for the tensors, convert that to OpenCV matrices, then call into whatever function we want to call in OpenCV, or this could be some other, for example, a lot of like really fast like matrix factorization libraries or linear programming libraries are usually written in C++, so you could just call into those and then just wrap that back into a tensor that we understand. Then all you need to do to bind that into Python are these three lines here at the bottom. And then to convert that into a Python module, we have two options. You can either use the left version where you write a very tiny setup.py file, like you would for like a Python package, where you create the CPP extension object, you pass it a name and the source file, and then when you run Python setup.py build, you get a Python module that you can import into PyTorch and then use with your normal PyTorch code. And then an even simpler mechanism is what we call just-in-time extensions, where you can actually embed the compilation of your model into your training code. So this could be like at the top of your model, and then the first time this runs, it'll compile the extension in the background for you and then import the Python module into Python. And the end result of this is that you can really like import PyTorch, and then you can also import your extension as a Python module, and then you can call into the C++ function with PyTorch tensors, with PyTorch models. It really feels like a Python function, even though it's written in a much more high-performant language like C++ or even CUDA, which is really great if you like want to write a participate in a Kaggle competition and outclass your competitors with some cool CUDA function. And then even more briefly, because I know this is kind of getting really far out to what most PyTorch users would want to do, the C++ front end. So the purpose in life of the C++ front end is to provide the aesthetics of PyTorch in pure C++ to enable research in environments that are quite constrained. So environments that are low latency, like a game engine, or bare metal, where like you can't have any Python involved, or multi-threaded, right? We all know that Python has the global interpreter lock, which makes threading a nightmare. So in those cases, this front end is a really good alternative. And also, you might have an application that's already in C++. So I was at CPPCon a couple of weeks ago, and there, for example, there's companies working on stuff like Autodesk, like a 3D imaging software, all of that in C++, and they also want to do machine learning. So of course, if you already have a huge C++ application, getting Python into that is really hard. So they want a solution that's purely in C++, but allows them the same flexibility as Python. So this is where this also becomes really useful. And we generally provide the same things as in Python. So we have a neural network library, we have a library of optimizers, we have data loaders, serialization format, and then on top of that, we have interoperability between Python and C++, and also interoperability between C++ and this script language that we newly developed. And now the cool part is what does this actually look like? So as you can see, the C++ code on the left, and the Python code on the right really look as familiar as we can make it, next to like the differences in the syntax of the two languages. But generally, we have like very similar concepts like modules, and we have the same kind of layers, like fully connected layers. And then the implementation also uses tensors like in Python, and the code itself looks very similar, which means if you have to transition from Python to C++, we make that very, very simple. And the same goes for the training code, which really looks like even more similar. So we have data loaders in C++, we have optimizers. The training loop looks the same as well. So if you have to go from Python to C++, it's really simple and intuitive. And yeah, that's all I have for now. I'm happy to take questions about more about PyTorch, about the PyTorch 1.0 production version, the PyTorch C++ interface, which I work a lot on, or anything else you want to ask me about. So yeah, thank you for listening. Yeah. Oh, you wanna? Okay. Yeah. That's a good question. So, a lot of you might have heard about Onyx, and so this kind of feels like something very similar. So we're kind of transitioning to actually splitting Onyx into the two parts that it currently is, which is, for one, a standardized representation of a neural network, kind of like just a standard for that. And then on the other hand, what it currently also is like this, like a converter between various different frameworks. And so this step from PyTorch to Caffe2, which currently Onyx does, we're actually trying to merge into what we now call the torch.jit interface. So we want to be able to really just convert PyTorch models to Caffe2 directly, and actually, so Caffe2 recently merged into the PyTorch framework, so there's now a Caffe2 subfolder of PyTorch. And so the long-term goal, in a year from now, Caffe2 won't really be a thing anymore. Instead, it'll just be, PyTorch will just have a really native graph framework, and then the Torch script language will be the interface between PyTorch and Caffe2, or like this graph interface in the back. And then Onyx will become more of this interface that you can, hardware vendors, for example, NVIDIA or Google TPUs can implement in order to support the various frameworks that also implement Onyx, like PyTorch or MXNet. And so to answer your question, the TorchJIT is becoming this conversion process, and Onyx is becoming more of a pure language standard for neural networks. Yeah.
Yeah, it should be.
I think it worked, yeah.
What kind of performance gains should one expect switching to C++?
For the C++ front end, you mean?
Yeah, just in general. Probably you have some
Mhm.
experience just, converting models.
Yeah.
Maybe there's some gain 10, 20% or 10 times, I don't know.
Yeah. There's like two ways of C++ here. Right? For one, we have the loading a PyTorch model in C++ just for inference, and then there's this whole other thing, which is the C++ front end. So it is a good question because at a fundamental level, the Python front end and the C++ front end would actually be very similar in performance because everything that PyTorch does that is any kind of computationally heavy operation is already implemented in C++ and ends up calling to like cuDNN or like is implemented in CUDA already. So in that case, actually, like most of the heavy operations are not going to be faster in C++. One thing that is faster in C++ is just the language itself in the sense of like control flow. For example, like loops are notoriously slow in Python, so whereas they're not in C++. So for example, this model that I mentioned that is this tree traversal is actually implemented in the C++ front end because doing recursion and loops is really slow in Python and fast in C++. So for also for like reinforcement learning that generally is very control flow heavy, you can expect some gains. But for like your run-of-the-mill like Resonance 50, there's like going to be zero difference between Python and C++, which is nice, right? Because we want to prefer Python, and we still also like even though I implement the C++ front end, I still tell people like if you can use Python, you should use Python, and that's always going to be like more intuitive than C++. But we're just providing like a pure C++ alternative for those people who can't use Python or want to use C++. So that was the first question, or the first part of this. The second thing is why export your model into like a Torch script serialization, then run it in C++. That's useful if you have like a pure C++ deployment environment where you don't want Python in the loop. And it's also going to be, so maybe not at the moment, but certainly in the future, we want this to be faster because we can look at the graph and do optimizations on it. So already now we can do like operator fusion. So if we see that you're doing a multiplication and then an addition, we can fuse that operation to a single CUDA kernel, for example, and then only have a single CUDA kernel. So in that case, this compilation step will make things a little bit faster. Yeah, sure, yeah.
So if you want to change the number, which I'm thinking your tutorial, if you move from Python to C++ for an LSTM-like function is about 10%.
Right, yeah.
And 20% percentage points to write it.
Yeah, Thomas works a lot on the C++ parts as well, so yeah, he would know. Yeah.
Do you provide something similar like the TensorBoard?
Yeah, it's a good question. So actually, so TensorBoard kind of has managed over the years now to become a bit detached from TensorFlow itself, and TensorBoard actually natively supports PyTorch now. So there's a couple of people at Facebook and also at Google collaborating on this, and you can actually use it quite productively now. So you can have all your visualizations, all of that, with using PyTorch. Another thing which Google recently announced was TPU support for PyTorch, which is also a really nice addition. So we are kind of collaborating on a couple of these things and making like getting some of the benefits that the TensorFlow ecosystem has also for PyTorch. Yeah. Yeah, and those things we actually try not to be too fancy in that sense because we really want to make sure that the C++ front end is as easy to use as C++, which means, for example, an important thing is, so if like a C++ expert were to write a tensor class, the first thing he would do is templatize it on the size, and then like everything becomes a huge template, and you end up with something like Eigen, which is you need like a PhD to program in. So it becomes really complicated, whereas like PyTorch, even in a C++ interface, has always opted for like a simpler approach. So I think like the answer to that question is more like we try to like kind of keep the benefits of PyTorch in terms of simplicity. At the same time, you still get like type safety benefits because, for example, just this forward function here has to be a tensor and can't be like I don't know, like a function or something else in Python. So you do get some type safety from that. Yeah. Yeah. Right, yeah. Yeah.
So first part, are you still planning to use Max as
Yeah, so the first question is, yeah, so on the Onyx serialization and the PyTorch serialization will still be compatible in the future. So we'll try to like keep those compatible as I wouldn't expect that to work. So what we're more aiming for is kind of the PyTorch serialization format to be like a superset of the Onyx format. So it's kind of, you can export it into Onyx, but it wouldn't work the other way. And then the second question about the whether training would help. I guess it would help because you get the same benefits for like operator fusion and like quantization and other things we can do on graphs. So yeah, you could totally also do your training with the compiled models, and that might make it faster. It won't be as intuitive to write as eager mode. But if you want like some performance gains and you notice that you do get them from the JIT, then you could do that, yeah. If you are not planning to export on NX, how would you save the they get saved as part of the Onyx serialization format. Yeah, so the PyTorch serialization format is going to be a superset of the Onyx protobuf, which means like PyTorch in C++ will understand it. Yeah. Yeah, exactly. Yeah.
Okay, hi. Thank you for good introduction into PyTorch and so on. I have two questions. Basically, one question: are there any plans to make these graphs available explicitly in PyTorch? Because you mentioned that there are like possibility that internally you are still kind of computing this stuff. And the second question is: are there any plans about preparing maybe or making PyTorch available also in a static way? I would say this is functional programming paradigm way. While, as you mentioned, there is a problem with optimizations in case you use the eager mode, and it means in case you go to production, the optimization becomes more important. So maybe it's worth to think about like providing PyTorch interfaces also in like in static context as well.
Okay. Yeah. So for the first question about, so why would you want the graph exposed in Python?
Analyze, I don't know, debug or many.
Yeah. So for debugging, so actually, if you have a script code, that function or that module will have a .graph property, which has like gives you the IR of the compiled graph. So you can look at it, you can see what we did in terms of compilation or like optimizations. So yeah, we make it available in that sense. It's just like you can't like do optimizations yourself because all of that happens in C++. We do kind of give a view into what happens. And the second question, I didn't quite can you compress it a bit?
Yeah. So were there any thoughts about like also developing the PyTorch in a so to say static paradigm like TensorFlow, where you explicitly work on the graph? Because in this case, when you like first prepare a graph and then compute it, it's possible to make some kind of optimizations on the side of the framework, because optimizations will be more important in case it's deployed onto production. Because eager modes does not allow this, because you just do on your way. It means that something that can be optimized will not be optimized potentially. Yeah. Right. So are there any thoughts about making an additional like flow in PyTorch in order to also fulfill this or fill this place?
Right. So have like a mode where PyTorch would look like TensorFlow in a sense.
Maybe not like, but maybe in a functional programming paradigm way or static.
And I see what you mean. I think at the moment we don't have a plan for that. Like right now, what we like about the Torch scripts approach is that we still have people writing programs. So you're still programming actual code instead of programming a graph, which is also kind of like if you've heard about the TensorFlow Swift project, that's also the kind of their approach. Like you want to write code instead of graphs. And then like the framework handles the graph parts for you. So I wouldn't be aware at the moment of like providing an explicit graph mode. That might also be a bit hard to add at the moment, but maybe in the future, yeah. Thomas? All right. Yeah, I guess, I mean, if you like, so Pyro, which is this probabilistic programming framework, apparently has this. I guess you could also like implement it on top of PyTorch by just making everything like functions, like lazy functions, which would be like evaluated lazily or something. So you could effectively implement TensorFlow's execution model on top of PyTorch if you wanted to do that. There's also Haskell and OCaml implementations of PyTorch, so they probably do that too.
Yeah, the question is, of course it's possible to do it in a lazy functional mode, but it doesn't, like, it means that the framework does not make use of it. You will not anyway do optimization because the framework was already developed for the eager surveyor.
Right. Okay. Yeah.
What was troublesome about using the old style Python scripts for production?
For one, for example, we really don't like deploying Python at Facebook because Python interpreters are like humongous beasts and they're usually slow. They're not multi-threaded, so they're generally not really suitable to the large-scale like production systems that we have. So that's just like a problem with Python itself. And then also, so like all the benefits we get from these, like this graph mode are like the optimizations that we can do, which we can't do with scripts. So it's kind of mostly all of those things that were on this slide here somewhere a long time ago. All of this stuff. So it's harder to optimize, harder to deploy, whereas static graphs are like easier to optimize, easier to deploy, easier to do post-processing with, and don't have all these like troubles of the Python interpreter, which are like no multi-threading, generally being slow, and other things like that. Also, like versioning, for example, like the Python, like having different Python versions is also kind of tricky.
Any plans to provide something like TensorFlow?
Yeah, we kind of have like, so there's nothing like started yet, but we do have like longer term like thoughts about how we can have something like that to like. We're like definitely thinking of something like integrating Flask, for example, since we already have like PyTorch is already like a really native Python interface, so maybe we can have some really nice like integration with Flask, for example, to provide like a REST API on top of your model. So like yeah, long term we do have thoughts about that, but there's nothing happening yet. Also, what I wanted to add to the previous question, like if you are using Python in production right now, that you can totally use PyTorch like that as well, right? And there are some systems like Instagram, for example, is written entirely in Python and Django, which blows my mind, but it apparently works. Same for YouTube, it's also written in Python. So if it does work, there's absolutely nothing stopping you from using Python and PyTorch, and that's totally cool too.
Okay, so a couple of last questions, and again, that's a microphone, it's not a token, so you can talk to it. Anybody last questions? No? Okay, now you're all scared. Thank you again for nice answers and nice talk.
Yeah.
We're gonna have 5-10 minutes break, rather closer to 5, and after we come back with the second speaker.
Sorry? Yeah, sure. Do you have just like? I mean, I don't know what is a normal one, but just like more old style.
Can I also steal your
Yeah, definitely.
Okay, awesome.